See Lindelof videos, optimization problem number 4 for calculus. Um, God, this is our fourth one, isn't it? So here's a right triangle whose hypotenuse is the square root of 3 meters long, and it's revolved around one of its legs to generate a right circular cone. This drawing would be provided to you. Find the radius and volume of the cone of greatest volume. Also provided to you is the definition or the equation or formula for volume of a right cone. Remember, the first thing we need to think about when we're doing an optimization problem is that we need two equations. We need a secondary equation and a primary equation. The primary equation will be the equation of the thing that we're supposed to optimize. When we're the words that we look for optimizing are greatest, least, minimum, maximum. In this case, we're asked for greatest volume. So your professor will definitely want to see that the volume of a cone, of a right cone, is equal to 1/3 pi r squared h, and he or she is going to want you to describe this or define this as your primary equation. You also need a secondary equation, often called a constraint equation. And the constraint equation, possibly you can see here in yellow, is that we have this right triangle, and it's constrained by its hypotenuse of square root 3. So I'm going to say that the square root of 3, I'm using Pythagorean theorem here, so squared is equal to h squared plus r squared. Please don't be confused about this h. This h is not for hypotenuse. This h is for height, so therefore it takes on a leg of a or b. So this is what we have. Your professor is definitely going to want to see you call this either the secondary equation, or if you're in applied calculus in college, he or she would want you to call this the constraint equation. So I'm just going to call this secondary equation. I'm going to go ahead and simplify this a little bit, this piece right here a little bit. And the square root of 3 squared is just 3, isn't it? So the square root of something squared is the radicand, that number in the inside. So now what I'm going to do is look at this. And as I look at my primary equation right here, I realize this is what I want to optimize. So I want to take the derivative of this. But if you look here, here's the issue that we're having, and I want you to keep this in mind. We have two variables here. We have the radius as a variable, and we have the height as a variable. So what I'm going to do in this case, you could do it either way, but in this case, I'm looking at this thing. I'm going to solve this equation for not just r, but I'm going to solve it for r squared. So I think we would get r squared is equal to, am I right here? Right. R squared is equal to 3 minus h squared, isn't it? So r squared is equal to 3 minus h squared. That's just, right? That's just my algebra here. And then what I want to do is sub into primary. So then I'll have one variable calculus to do, won't I? So I'm going to actually do it. I'm going to say that volume of my right cone is equal to 1/3. Be careful because I solve for r squared. So r squared is 3 minus h squared, isn't it, times h. Oftentimes I want to solve instead. I want to solve and leave r there. But in this case, it's just so much easier for me. And you could do it either way. And I really do recommend that you try it. And did I forget my pi? There's pi. Somebody was catching that. Sorry about that. I'm going to go ahead and multiply this h in. I'm not going to multiply this because this is a constant value. So I'm going to say that the volume of my right cone is equal to 1/3 pi 3h minus h cubed. Can we agree on that? Here what I'm going to do is this thing in the front is just a constant value. This is not product rule. As a matter of fact, if it's bothering you that bad, just multiply this thing in, this 1/3 pi to here and to here. I'm not going to waste my time with it. But I am going to take the derivative here with regard to height. So I'm going to take dv dh. If you're worried about naming this derivative correctly, just name it v prime would be just as good. So we'll equal, here's my constant multiplier here. The first derivative of 3h is just 3, and the first derivative of negative h cubed is negative 3h squared, isn't it? hopefully you can see that we have factors, we can factor out a 3 here. And the reason I want to factor out this 3 is because I can get rid of this 1/3. So I can say that dv dh, the derivative of volume with regard to height, is pi times 1 minus h squared, isn't it? Isn't that good math? Sure it is. I like it. I like it a lot. All right, so I'm going to keep doing my work here. Now, right, the whole idea here is to get a primary equation, get a secondary equation, get the thing into an equation that's of one variable. We did that. To take your derivative and then find critical values. And remember that when we find these critical values, that is when slope goes to 0, if slope goes to 0, let's say slope goes to 0 right here, this thing is either a minimum or a maximum, isn't it? So that's why we're looking for these critical values. So what I'm going to do is I'm going to ask myself, when is 1 minus h squared equal to 0? I'm going to get h squared is equal to 1. Going to get h is equal to plus or minus 1, isn't it? Well, we know the height can't equal minus 1, so h must be 1. So h is 1 here. If h is 1, check me out here. If h is 1 here, check me out here. I have this r squared here. So I have r squared is equal to 3 minus h squared. R squared is equal to, how could I have forgotten that so quickly? 3 minus h squared, that's really embarrassing. 3 minus h squared. H is 1. 1 squared is 1. R squared is equal to 2. Therefore, r is equal to the square root of 2. From here, I can go to my volume equation. Go to the volume equation, which says that the volume is 1/3 pi r squared. So r squared is square root of 2 squared times h. H is equal to 1, right? Solve this out, and we get that the volume is equal to 2/3 pi, oh gosh, and it's meters cubed, Will, right? Don't forget units. Good job, boy. Okay, terrific. All right, so hopefully this is helpful and you're able to do this. Remember primary and secondary equations. Remember to take the to get this thing to one variable. Once we have it to one variable in our primary equation, take the derivative, solve for critical values, evaluate if those critical values are reasonable, and move forward. Good work, you guys. If you have any questions or comments, please let me know. If you haven't already subscribed, please do.